Again, I just want to point out, this is something I'll talk about more in the next lecture. Most of the tasks we have in general in engineering can be written as optimization tasks, okay? Model reduction, you're trying to find the best model in some metric of, at some reduced rank R to describe your data. Control is usually posed as an optimization problem. Sensor placement, actuator placement, closure models, these are all optimization problems. The thing that brings them together, at least in fluids and in a lot of the systems of interest to modern machine learning, is that they're high-dimensional, nonlinear, non-convex, and multi-scale. So these are optimization problems that 20, 30 years ago we couldn't solve, even 10 years ago. And with emerging techniques, with better data, bigger computers, and better optimization algorithms, we can start solving these problems. Okay. Good. So I'm going to just walk through types of machine learning, examples of what's easy and hard in machine learning. Then we'll talk about neural networks, how you can model dynamical systems. If I have time, we might talk about some historical context of kind of understanding what's happening today in machine learning with respect to what has happened in the history of science. Okay, so I'm going to start here with types of machine learning. So we have some complex system. This could be maybe I have a self-driving car and there's a camera viewing the world in front of this car. Maybe this is my fluid dynamic experiment or simulation. It's just some system that's generating data, hopefully tremendous amounts of data, but not always, okay? And so the idea is that you're going to have some data that you're going to use to train a model. And there's a lot of different ways of slicing these machine learning algorithms. I'm picking one categorization, which is whether or not you have labeled truth data. Okay, so oftentimes when I collect my data, I know what type of data is. So I'm taking pictures, and if Facebook has all of your pictures, it got you to label them. Right? Oftentimes in the past, like you would click on who's in the image and you would type who that person is, and you would label that data so Facebook would know who was in that picture. Okay, so that's labeled data. Maybe you run a wind tunnel experiment for a new airfoil, you measure the lift coefficient. Okay, that's labeled data. Unlabeled data would be more like the self-driving car example, where you just have a camera and things are happening and you don't have someone expertly labeling what's happening. Okay? And so if you have labeled data, if your data has tags telling you the features that you care about, then that's supervised learning. Makes sense. And there can be continuous or discrete labels. So for example, if I'm trying to build a classifier to tell pictures of dogs from pictures of cats, there are only two labels, dogs and cats. Category 1 and category 2. That would be a discrete classification. And there's lots and lots of methods for discrete classification. Support vector machines, decision trees, neural networks, so on and so forth. If you have continuous data, like the lift coefficient example, then this would be a regression problem. Okay, so all kinds of different regression models. The Cindy model I told you about yesterday is a regression model. Gaussian process models are regression models. And so lots and lots to choose from. And one thing I'm going to point out a few times, I'll probably say this more than once, is that I want us to not get confused. Machine learning is not just neural networks. And don't let people tell you otherwise. There are going to be people, when you say you do machine learning or you have data, they want you to train a neural network. And that is the only worldview they have on machine learning. That's not what machine learning is. Bernd, yeah. I'm sorry?
Should I tell a couple of colleagues with this?
So what I want to do is I want to separate tasks from how we solve these tasks. None of these tasks are going to be build a neural network. A neural network is a tool that you can use to classify. It is a tool you can use to build regression models. There are many others, okay? So another categorization, if you have unlabeled data, so you do not know what data you're seeing, this is kind of the older, one of the older branches of machine learning is unsupervised learning. Okay, so this is classically called data mining. You have a bunch of data, you're trying to find patterns and extract meaning from this data, but no one tells you what you're looking for. So this is like searching for a needle in a haystack. Again, you can have discrete or continuous. Discrete unsupervised learning is called clustering. You're trying to find groups of data that behave similarly to each other and differently between groups. Okay, and you can also have continuous unsupervised learning, which generally I'm going to call embeddings or dimensionality reduction. So POD, proper orthogonal decomposition, and principal components often fit into this kind of unsupervised world. Okay, and I'm only listing a very few of the methods here. For example, 10 years ago, people didn't use neural networks for classification much. They weren't the best. Amazon used decision trees, random forests, support vector machines. Those are the industry standard methods. Yes?
So now you say that discrete data is classification data, but you can also have discrete data that does not belong to basically classification.
If your labels are discrete, it's a classification task. I mean whether or not your labels are discrete or continuous.
Because if I have lived discrete time, it's not classification, right? Can you repeat it for everyone? So my question was, if I measure lift, for example, in a discrete time, I wouldn't classify that as classification problem, right?
So I don't mean discrete time or continuous time. I mean whether or not your labels are discrete. If I am only trying to classify between pictures of cats and pictures of dogs, there are two distinct labels. If I'm trying to classify or predict what the lift will be on an airfoil at an instant, that can be any range of a continuum of values for the lift coefficient. That is not a classification, that's a regression task. Let me point out also, nothing I say, so maybe I should just say in general, a third of what you hear in machine learning is going to be bullshit at the very minimum. And so you get the fun job this morning of trying to figure out which third of this. If I get 80% of the way there, I'm pretty happy. I'm going to oversimplify. That's my job today, is to oversimplify things for you. Okay? Good. So the middle block, I think, is particularly interesting. This is where a lot of the most cutting edge research is happening in machine learning because, and there's actually a really interesting dichotomy between the successes of machine learning in industry. Think Facebook, Google, Amazon. They have mountains of labeled training data. And they have, it's billions of dollars, literally billions of dollars worth of labeled data that they got us to label for free. Okay? It's much harder as scientists for us to collect that labeled data. That costs money. Okay? And so a lot of work is going into what's called semi-supervised learning, where you have limited labels. You have an expert kind of semi-supervising your process. And it might be too expensive to label all of the data, so you label 1% of your data. Okay? And there's a few different kind of big categories here. I'm classifying them based on whether or not you want to model your data or actively modify your data, whether or not you are a free agent that can change the world, or whether you're purely a passive observer in the world. And so some of the really exciting ones are these generative models. The Mona Lisa picture I was showing earlier, that's a generative model where you basically have two kind of, in this case, neural networks or learning algorithms that are fighting with each other. One is trying to trick the other one. And so it's semi-supervised in the sense that the neural network itself is supervising another neural network. Okay? Reinforcement learning is a really interesting class of optimization where you are actively trying to change how you interact with an environment. So you can think about the game of chess. Okay, you are learning the rules, you're learning your opponent, and you're trying to design a control strategy to, in some sense, maximize some objective function. Okay, and so you can also then take what your model of the system and make decisions that then change the system. Okay, that's a pretty interesting perspective, and that's something we should all be thinking about because we're not just going to be classifying images, we're trying to manipulate our system. And you can also do this with fully supervised learning with just generally optimizing and controlling your flows. Okay, good. Okay, so that was like about as shallow as you can get in terms of classifying machine learning algorithms. Again, I want to point out there are tasks, there are the quality and quantity of your data, and then there are methods of actually solving the optimization problem you're trying to write down. And those are three different things. Okay. So when I talk to like executives about machine learning, I always give them this little spiel on what's easy, medium, and hard, because that's probably the hardest thing for people to figure out when they're just learning about machine learning. You see all of these examples, and it's not obvious what is possible and what's not possible. What would take one afternoon in TensorFlow and what would take 5 years with a concerted research team and millions of dollars, okay? So it's this nice XKCD. Maybe some of you have seen this. So telling whether the photo contains a bird, this was actually pretty old because it's now easy. This was hard a few years ago, labeling what's inside of an image. But you know, if your data has a geotag, it's pretty damn easy to tell where it came from. Okay, like it's all about what's in your data and how hard your optimization problem is. Okay, so image recognition, facial recognition, this is one of the original successes of machine learning. This is kind of why, honestly, it's why we're in this room today. It's why in the last 10 years so much attention has been given to this, is because finally machines can classify images about as well as humans can. Maybe not in every circumstance, maybe not as reliably or robustly, but it really is approaching human level performance. Facebook can tell if two people are the same or different about as well as you can. Okay, pretty remarkable. Interestingly, they don't do it by just taking two-dimensional images. That gets you about to below 95% classification accuracy, but humans are upwards of 97, 98% ability to tell who's the same and who's different. Any ideas how Facebook cleared that last 3%? Which is always the hardest. Sorry? Okay, so that's a great one, is they have some idea, some prior of who you would possibly be taking pictures of based on your network. That's definitely true. But they do this test on, so the same different test is for complete strangers. People you don't know, can you tell if they're the same person or a different person? So what would get Facebook up to that 97, 98% accuracy? And again, this was 5 years ago. So yeah, so they're already using color depth. So they do a few things right off the bat. The first thing they do is they will take your face, and there's pretty good algorithms to find corners of the eye, corners of the mouth, and corners of the nose. And what they'll do is they'll stretch your face onto a regular grid, because everyone has different geometry, and you can't compare people's faces if my eye is where your nose is. So you have to stretch everyone to a common grid. That's step one. They've been doing that for a decade. Step two, they actually estimate the geometry, the structure of your skeleton, the three-dimensional spatial geometry. That's how they cleared that last 3%. It's a little creepy. They're modeling your skull. So you see this picture here, you as a human have a pretty good idea that that is a three-dimensional nose that casts a shadow, and that's extra information that you can use to classify. Okay, so that's this additional understanding of the world that was very, very difficult to learn. But that's what got them to clear the gap. Okay, so image classification is a huge deal. This is just a tiny, tiny, tiny excerpt from the ImageNet database. So how many of you have heard of ImageNet? ImageNet was this, I forget how many, 10 million labeled images, hand-labeled images, something like 10,000 categories of images with thousands of examples for each, like 1,000 pictures of broccoli. Labeled broccoli, 1,000 pictures of tractors, labeled tractor. Humans did this. This was one of the most impressive data sets collected. And that large data set was what allowed these new neural networks to be trained with such high accuracy. So again, machine learning does not start with a neural network. It starts with a mountain of quality data, usually. Okay? You can zoom in and see there's all kinds of stuff in this, and there's thousands of examples of everything. Okay? And so image classification 15 years ago was very difficult. Now it's almost trivial. We take it for granted. Okay, you can hold your phone up practically and classify an image. This one's really cool. This one actually fooled me. I thought I gave this talk a few times before I realized that these were actually misclassified. Like, these are generated images that were generated to trick a classifier. So these are pictures of my broccoli, my tractor, some purple flower. These are generated images from that same statistical distribution. I don't know if you can even tell the difference between some of these tractors if you're sitting in the back. Maybe you can tell that this broccoli looks really not edible. But it's kind of amazing that you can now generate images. That's pretty cool. Okay, but it's not perfect. This is the cutest blueberry muffin I've ever seen. I mean, it's not difficult for you to tell the difference, right? Everyone in this room, I see some people squinting, everyone in this room can tell the difference between a blueberry muffin and a chihuahua, okay? My sister just got a fried chicken dog. He's adorable. But this actually still is challenging because machine learning algorithms build models based on the features that they have. They don't have legs and arms and a body to go carry them through the world and build experience. They do have ancestors now, but they don't have, generations of knowledge and modified neural networks like we do. We have an understanding of the world that goes much deeper than what our simple machine learning classification algorithms understand the world in. Now these algorithms are being deployed at scale. This is another thing you have to think about is just because you can demonstrate that something is possible, can you make it robust? Can you make it streaming, real-time, scalable? So now, with self-driving cars and surveillance, these image classifications are running concurrently in hundreds of thousands of platforms all across the world right now. Okay, so it's a little scary, but that's the world we live in. Is that this is now ubiquitous. This one's pretty cool. Image captioning was for a long time thought to be impossible for machine learning algorithms. And I think within the time I've been giving this talk, this became possible. So this is image captioning. You can give Google a picture of a scene, not just a piece of broccoli or a tractor, but a guy playing a guitar, and it will caption that image for you. Pretty neat. Of course, it's never perfect. This is probably my favorite one. This looks like where I'm from in West Texas, and you can see that there is no horse. But it's pretty remarkable, and the performance here is surprisingly high. Okay. Atari games. This one is really neat. You can use these reinforcement learning algorithms to build models of whatever virtual world they're given data. So this is the Google DeepMind reinforcement learning algorithm. They're given the pixels in classic Atari games. Okay, so just like when we were kids, we played games until, we couldn't see straight anymore. So does Google now. This is Blockout. And you can see this is literally it just learning how to play the game. It has some idea that what it wants to do is make these numbers big. Okay, so someone tells it what the objective is, and now it knows that it has some control input, and it's just going to futz around until it can figure out what to do. Okay, after 2 hours of training, it's actually quite impressive. It's playing better than I could. It's a very simple game. This is its entire world. Its entire existence lives inside of this box. So that's a little sad. But something amazing is going to happen. So after 2 hours, it learned to play, but after 4 hours, something really, really special happens. It learns the trick that only... Ooh. What happened? Yeah, you're going to have to wait. This is the suspense. This isn't... So I've been making fun of machines for years, and I think they know. Good. That's okay. Let me skip to the actual part of the movie so you don't have to watch this again. Okay. Good. Okay, so it's playing like an expert. And after 4 hours, you're going to see the transition. So remember when you were a kid, and I don't know, this was before the internet when I was a kid, or before everyone had it. There was one kid in the neighborhood who could just destroy everyone. Okay? That's this Google DeepMind. Look what it's doing. It's going to find a weakness. It's going to dig a hole. Come on. There you go. And now it's all, like the game plays itself. Did you see that? It's amazing. It learned something. I mean, this is a simple world where it can. There's one trick, and it learned it in 4 hours. It's pretty impressive. Now, there's actually a really great paper. I forget if it was a science paper or not, but you can download this original Atari deep learning Min paper. And there's a list of which Atari games it could totally destroy and which ones totally destroyed it. And it's really interesting to start thinking, does everyone remember Asteroids? Simplest game ever. You turn right, you turn left, you fire, and try to destroy asteroids. It could not play that to save its life. For some reason. I suspect it's because of rotational and translational invariance, which is really hard for machine learning. Okay, but it's not all about playing games. You can also teach robot machines how to do human tasks. So this is the catch in a cup task, right? You swing a ball on a string and you try to catch it in a cup. So when we were kids, we played this game. And this robot, you can see it's trying. It has to have a white background and a high-resolution camera trained on it at all times to learn anything. After 15 trials, after 25 trials, close. Probably can't untangle itself. But this is about how long it would take a kid. Like if you had a 10-year-old trying this, it wouldn't take them, it would take them between, 50 and 100 trials probably. There you go. It learned how to catch in a cup. Now this is its entire world. It's not doing anything else except for this. But, and this is interesting. It requires some knowledge of physics. I believe they probably baked in some rudimentary laws so that it could learn the physics it needed to. This one I think is pretty fun. This is a video my friend Ed Lazowska showed me. It's a DARPA video just showing how advanced our robots have become. I mean, robotics is really hard. We take for granted how seamlessly we walk. This wasn't that long ago. This is 2015. So Ed likes to joke that in the robot uprising, all you have to do is hide in the bathroom, but you don't have to lock the door. Yep. So it's still quite challenging. Yeah, Bernd.
Robots who are really amazing.